Get the steering using sinusoids. So you have like this is Q1, which is directly actuated. This is Q2 directly actuated, and we want to move from the origin somewhere along the z-axis, which is not directly actuated but actuated by the lead bracket. We did it using sinusoid. So U1 was cosine and U2 was sine. So this means that in that plane Q1 and Q2 will make a circle, right? And while making the circle, so the three-dimensional version of it will be something like that. So making the circle, and while making the circle in that plane, it goes up some distance in that direction. And actually this distance is related to the area, right? It's twice the area that is covered. If you want to go up more, cover more area, it's actually double the area, right? Any questions about that? But this was for a specific class of systems, like we talked about this class of systems that Qi dot is directly actuated and Ij dot is actuated by first order Lie brackets, then Ijk actuated by second order Lie brackets, right? And we also talked about chained systems. So we talked about Q1 dot is U1, Q2 dot is U2, Q3 dot is Q2 U1, and so on. So Qn dot was Qn minus 1 U1. So again, with this interesting notion that you do a loop in the plane, but you get a net motion in a new direction. When we applied it, we did not discuss, the implication of this problem. Last time we talked about this problem mathematically. So we have a robotic arm here that we can extend. So we have L as a function of time. It's our control, and we have also its attitude as a function of time. It's another control. But as a result, we get a control over theta, the angle of the body. So you have you have this robotic arm that you move up, that you move back and forth. You can move back and forth, and you can rotate sideways, but you cannot rotate the body. And as you do the following, you rotate your arm and extend it upward, and then bring it back and extend it inward. The net result is a net motion for the body, right? This was the Lie bracket between L input and the psi input. We get a motion in the theta, and the Lie bracket is implemented by cosine and sine. So this guy is cosine, for example. This guy is sine. So this guy is cosine. So we start with some value and decrease it. So say move in this direction while extending it, then moving back while retracting it, right? And there is a phase shift between the 90 degrees because one is cosine and one is sine. The net result is a theta motion. So this was a good strategy. It allows you to do the motion in one cycle. This is the minimum energy. But if you do it in one cycle, it means it's the slowest possible, right? Because I can do cosine and sine faster, but it will take multiple cycles to get to the final point. This is not a minimal energy solution, it's a solution, but it will give you smaller excursions in the other direction. If I want to move, for example here, if I want to move just in theta, not in psi and in L, well, but I have to move in psi and L to get a motion in theta. So if you want to do the minimum energy, then I will have long excursions in psi and L to get my motion in theta in one cycle. But if I want to do that with minimal disturbance in psi and L, then I have to do it much faster, and I'll get to the final point in multiple cycles, not one cycle. Then the disturbance in psi and L will be small, but the energy will not be minimal. I will operate at higher mode, not the first mode. At any rate, these are the physical implications of this steering algorithm, but as you can see from the system, yes, it may cover a wide class of system, but it looks quite confined. So today we're going to talk about another steering algorithm, and the lecture is a bit mathematical. So it's motion planning, and for a more generic form, motion planning for driftless. So we're going to talk about driftless in general, not a specific form, but will require the system to be nilpotent. We're going to talk about that in a minute. Driftless nilpotent systems, okay? So we're pretty generic. It's our form x dot equals summation j equals 1 to m gj of x uj. I have m vector fields. X live in manifold n-dimensional. Maybe it's Rn. So what do we mean by nilpotent? So nilpotent system of order k is so all Lie brackets containing k plus 1 and higher vector fields vanish. For example, we have, say, two vector fields, m equals 2, so g1 and g2 only, and we have k equals, say, 2. So this means that this Lie bracket g1 and g1, g2, this guy vanishes because it has three vector fields, as well as this guy as well, completely vanish. These guys completely vanish. I mean, it doesn't have to be k equal to any k, give me any k, but you have to guarantee that after some point of differentiation, these guys will vanish, okay? This is the type of system that we're gonna talk about today, and this is the work by, say, Lafferiere and Susmmann. Susmmann is one of the finest mathematicians in the country, Rutgers. This was 1991. Motion planning algorithm by Lafferiere and Susmmann for driftless nilpotent systems. Can be nilpotent of any order k, okay?
Professor, should k, the value of k should be less or equal to m? Or
say it again, I'm sorry?
Should the value of k less or equal to m?
M is the number of vector fields, and k is, you can say, number of differentiations.
So there is no relation?
Yes, there is no relation. So what if I don't have an nilpotent system? Well, like the kinematic card, for example, is not nilpotent because it's cosine and sine. You can get differentiation forever. Well, so these guys, Herms, yes, 84 and 89, they showed, at least for this system, x dot equals, so g1, u1 plus g2, u2, only two input vector fields, okay? If g1, g2, and their Lie bracket are linearly independent, which is the case, linearly independent at the operating point, at x naught, which is typically the case, then there exists some transformation. Say u can be transformed to w, so this is transformation as a function of x. New inputs w, such that in the new inputs x dot will be something like g1 tilde w1 plus g2 tilde w2, and this is nilpotent system. Okay?
This is a linear transformation?
No. What do you mean? Linear transformation in the inputs, but it's not linear in the state. Nilpotent. Okay? So this is what we call nilpotentization. So there's some work in the literature about nilpotentization, if you can do it or not. And even if you cannot do it, you can still approximate your system by a nilpotent system and work for the approximate system step by step. At any rate, let's focus on nilpotent system and see how we can do the motion planning here. Any questions so far? Any questions? So, remember our Lie infinity of the set of vector fields. Now they are exactly equal to the Lie up to k, because all k plus 1, they vanish. Right? And you remember that this guy was a Lie algebra. What do you mean by Lie algebra? It's a vector space, right? And it has a Lie bracket. So a vector space, and it's finite dimensional now because we have finite vector fields and we do finite differentiation. So we can talk about the basis, right? So vector space, let's talk about the basis. I'm reminding you that the Lie bracket like G1, G2 versus G2, G1, these guys are the same, right? It's just a negative sign, so it's not providing any new direction. Irrespective of G1 and G2, right? So I'm talking about the algebraic structure, just from the perspective of algebra. And also, because Lie brackets by definition must satisfy this property, the Jacobi identity, G1, G2, G3, and keep rotating. So this is G3, G1, G2, and G2, G3, G1. The result is the zero vector, right? For any, I don't care about these G's, how they look like, right? From a Lie algebraic structure, this guy is zero, which means is one of them is linearly independent of the other two. One of them will never provide any new information. So in my basis, because basis by definition have to be independent, linearly independent, I must exclude these guys, right? I must exclude the things that are linearly dependent on the others. And one way of doing that for Lie brackets, irrespective of the vector fields, is called P whole basis. So this is the basis of the Lie algebra, Lie k of G1 up to Gm, and because it really doesn't depend at all on these guys, it just needs a bunch of variables, right? And the Lie bracket definition. So it doesn't have to be for vector fields, it's for anything, for any Lie algebra of some variables, m variables, with some Lie brackets. So this is much more generic than vector fields. Some people denote it by Lk x1 up to xm, and they call the x's indeterminates. Indeterminates mean to be determined later. We don't care about their nature. They can be vector fields, they can be matrices, they can be polynomials. It doesn't matter as long as they live in a Lie algebra. Okay, can you please provide me the basis for it? So as you can see, the basis depends on the number of elements, m, and the order, k. So this is, we're gonna give it the symbol, mathcal b or something. It depends on m and k. So for example, m equals 2 and k equals 3. What is b, 2 and 3? What's happening? Why is it doing like this? Okay. Well, so we're gonna be, so we have here m, the two, you call it whatever you like, x1, x2, g1, g2, x and y, whatever you like. So it has x and y, right? It has the Lie bracket between x and y. Obviously, I cannot include the negative of the Lie bracket because it doesn't provide anything. We have x and y, and we have y, x and y, and that's it. For these two guys, I cannot include the third because it's linearly dependent on them. And then the next level vanish because k is 3. Okay? So another example, say m equals 2, k equals 5. This is pretty involved and needs careful construction. You don't need to worry about them at all. Just Google p-hole bases. You will find codes to generate them for you. Here is, I can give you, not here, no. Where is my lecture? There. Ah. So, yeah, sorry about that. I will get you the thing. Okay. Here. Lectures. So this is the thing. Yeah, here we go. Take a snapshot. These are the guys. These are the bases, the p-hole bases for m equals 2. So we have two vector fields or 2 entries, and we have differentiation up to 5. So b of 2 and 5 is these guys, which I'm gonna paste now. Any question about the p-hole basis or whatever we have been discussing so far? The lecture is a bit mathy, so don't let anything, because they're going to accumulate, they're going to build upon each other. So if you have any issue, just stop me and we can discuss it, okay? I'm trying to make it as simple as possible. So even in the book of Sastry, they complain about the difficulty of this algorithm. So anyway, but hopefully it will be clear today. So, so we got the p-hole basis. So let's see how we can do the motion planning of this guy, if it's nilpotent. So you have x dot equals summation j equals 1 to m gj of x uj. Obviously, this system must satisfy the log, otherwise we should go home, should not do anything. The log is necessary and sufficient for controllability here. Satisfying the log. What do we mean by satisfying the log? We mean that there is a span of some vector fields. These vector fields are g1 up to gm, right? And some Lie brackets, so gi, gj,